What do you?
Hey there, Eights. I just finished marking your guys' assignment on this day, on the 30th of April, this combining transformations assignment. And then a couple people got to the matching, which is great, and I tried to give good responses to the matching. It worked really differently than it does when we do it in class. But this is the one I wanted to talk about specifically, and it's this assignment where we have this shaded triangle, and in number one, we're doing these things to it. So I'm going to color code my responses. Here's the colors I'm going to use. Yeah, let's just go ahead and go. So question 1A then, we want to translate -7 horizontally and +1 vertically. A lot of you have this idea right on that we're starting here at those 3 points, and we want to go then left 7 and up 1. So I think almost everyone, if not everyone, took this point, left 7 and up 1, and had a point there. But some people just stopped, and I know that shouldn't be, it should be a point, not like a cross, but I'm just not as good with the mouse. So then these other points should also translate. So this point would also translate left 7, up 1, and I would end up with this point here. And then the last point here would translate left 7, up 1 to this spot. And so we'd end up with this triangle. It looks like that. That would be triangle A. Then, because we label our answer A. So for B, reflect over the x-axis. Well, x-axis is here. So if I take this point and reflect over the x-axis, it goes 2 units to get to the x-axis. So 2 units past, it ends up here. Same thing with the other points. This goes 4 units, so 4 units past should be here. The other one, 5 units, so 5 units past ends up here. There's B. And I'll try to go a bit faster because I know, well, actually I shouldn't because the rotation is the hardest one. So next we want to rotate 90 degrees clockwise around the origin. So origin is here. We want to go, where's my mouse? We want to go clockwise, which is, I always have to think, this direction, 90 degrees. So if I connect this, I can ballpark 90 degrees. And then I can picture this as being 1, 2, and I can see this line is kind of pointing at 2, 1. It's out here. But then the other points would do the same thing. So if I go out to this point here, that line ballparks over to here. And then I picture 3, 4. So this line I can see going towards like 4, 3. Wait, am I right? This line, no, it's pointing down at 3. No, I think I was right. It's got to be 4, 3 over here. We'll see at the end when I finish if it makes sense. So let's do this third point. That third point is hard. I'll just go to black because it's getting messy. So that third point then, I'm to the left of those lines. I should be like up there somewhere. And then I can see 2, 5. So it's going to go 5, 2 to here. And puts that point there, and then this triangle does connect and make sense. Like it's hard to see in the middle, but that would be triangle C in blue. And then reflected over the line y equals x for part D. Well, the line y equals x has a gradient of 1 and a y-intercept of 0. So we're looking to start at 0. Gradient of 1 is perfectly diagonal. And I know that's not perfect. But then if I'm going to reflect here, this is only going half a diagonal box to get there. So I'd only have to go half a box across. That's where it ends up. This one also, half a box, so half a box across, we end up there. And this one's going a box and a half diagonally. So I'd have to go 1.5 diagonal boxes to end up here. And we'd end up over here. So that's a diagonal reflection, and some people were mixing those up with rotations. And I understand why, like they both change orientation, but in different ways. You can see going from the red triangle to C, like it rotated, so kind of this point thing is still pointed up. But when we go to D, it like reflected, so that point thing is kind of down, if that makes sense. Then, okay, let's look at these other ones. We want a single transformation that takes the red triangle to E. So I had a lot of people talking about ideas of rotation here. Come on. And I totally see why, because that kind of looks like it rotates around to there. But if I take one single point, you can see it doesn't. From there, if I rotated 180 degrees, that line would be straight. I would end up here. So it means that this can't be a rotation that ended up there. What you're looking for, if you'd said that, and I guess first, before what you're looking for, one way you could notice is if this thing rotated, we'd still have like that pointy piece going, like it was up here, it would rotate and now be pointed down. But that pointy piece, like that's the part I'm talking about, it's still pointed up. So it's not a rotation. It has to instead be something else. And in our case, we're looking for, if I draw a mirror in perfectly diagonally there, you can see these things reflected across here. So it is a reflection in the line y equals negative x. So that's what you should have here. And a lot of people were talking about the idea of 180 degrees, which makes sense, except this is not a rotation. And if it's not a rotation, we shouldn't be talking degrees. We should be talking where's the mirror for the reflection. So then if we want to take the shaded triangle onto F, we're going around here, I can picture like that point rotating, and now it's pointed out this way. Before it was pointed like up that way, if that makes sense. So there I can see that rotation, and people had good descriptions for that. The very last one. So we have two separate things happening here. We're going to rotate 90 degrees clockwise and then reflect over the x-axis. I should say the whole thing, 90 degrees clockwise around the origin and then over the x-axis. So 90 degrees clockwise around the origin is what we did in C. And if I just go back and look, C ended up out here. I can picture that, I can see that. So now I'll just bring that back. C is at one, oh, come on. Again, I have to kind of ballpark it. So it's there, this one out. So that's 3, 4, so this should be 4, 3, yeah, like that, I think. And then we're going to reflect in the x-axis, was it? Unfortunately, I have to go look. In the x-axis, let's see if I can put that back at the origin. That's about as close as I'm gonna get. Then in the x-axis here, so if I then take that, this is like step 1. Ah, come on. Sorry. This is like step 1. Now step 2, reflect in the x-axis. So I'm going to take that image, and the image, the blue triangle, becomes the pre-image for this last one. And when I reflect, that's going 4 units, so 4 units past, it's there. This one is going 3, so 3 past, it's there. So I end up with this purple triangle. Now, if I look at that red triangle and I want to get to that purple triangle, this to me just looks like I can see a vector translation there. It's just going a little bit down and right, which means I also probably screwed up the rotation. Is that point supposed to be there? Would make it here. That seems more reasonable. So that's the type of thing I'm looking at in this case. If we take this and rotate and then reflect, you see we end up with a translation that just works like that. So that's just to say, if we had some sort of application in a computer running saying we want to do some things, and some of those things are rotate and then reflect, and rotate and then reflect, and rotate and then reflect. Well, that's 2 steps for every operation. We can remove that and just do a translation. It's much like it's literally half the processing power on your computer, which means your application runs twice as fast. So just to say that if we have multiple transformations, we can usually cut them down. I'm probably already talking too long. Thanks, Ates. Best of luck. Talk to you soon. Bye.